a little bit more about electric fields. First, a little bit more about how we can think about the net electric field from a bunch of sources. And let's say, in this case, let's look at my notes. So we've got three charged things all in a row, just to keep it simple. So there's something with 2 units of positive charge, and then there's the point where we're going to think about the net electric field at that point. And then 1 unit of positive charge here, and then 3 units of negative charge way over there. So we know that the net field at x is a sum of 3 fields, the field caused by this one, the double positive, plus the field caused by this one, the 1 unit of positive charge, plus the field caused by this one, the 3 units of negative charge. So think about directions first, and that, in other words, think about the signs of these things. Put a positive charge here, it's going to feel a repelling force from this positive charge. Positive charge here would then feel a repelling push to the right. So the force on a positive charge here is a force to the right coming from that. So at this point, the field that comes from this is a rightward field, pointing in the same direction as the force on a positive charge. So positive. And then here's another positive charge. If we put a positive charge here, again, it's going to feel a repelling force. A positive charge here is repelled to the left by this thing. So the force that comes from this thing, acting on a positive charge here, is a leftward repelling force. So leftward is negative. And then finally, this thing, put a positive charge here, it sees the opposite type of charge over here. So opposites attract. So a positive charge sitting here would feel an attracting force from this. That is, a positive charge here would be pulled to the right by the force that comes from this thing. So the force on a positive charge here at x, force coming from this as the source, is a rightward force. So the field at x caused by this is in that same direction as the force on a positive charge to the right. Positive. Okay, and then the magnitudes. Again, just to keep the algebra simple, we say 1 unit of charge 1 step away causes a field whose magnitude we'll call just plain E, and then fields of all different sizes will just be some fraction of E or some multiple of E. If there were 1 charge, this is 1 step away, then this would give a field that with a strength of E at this point, but there's twice as much charge, so the field has to be twice as strong, 2E. Remember that the field strength is just that K factor times magnitude of the source charge divided by square of the distance. So when the source charge is 2 units of charge instead of just 1, the field is twice as strong. Okay, here, 1 unit of charge 1 step away. So that creates here, 1 step away, a field that has a magnitude of just plain E. And it's pointing to the left in the negative direction. And here, well, there's 2 things going on. That if you you start with a field that's this strong, E, and then you go twice as far away, that cuts the field strength down to 1/4 of E. E was the field that you'd get from 1 unit of charge 1 step away. Then 1 unit of charge twice as far away, 2 steps away, has only 1/4 as much field, 1/4 E. That's 1 unit of charge 2 steps away is 1/4 E, but this is 3 units of charge, so 3 times stronger than that. 3 times 1/4 E. So 3/4 E. And what do we get when we add them all together? 2E minus E is just plain E. So we have E plus 3/4 E, or 7/4 E. Just a little bit less than 2E. And that's a positive number indicating that the net field here is a field in the positive direction. Because of all these charges here, if you put a positive charge here, because the net field points to the right, the force would be a force pushing and pulling a positive charge here to the right. Right. The one new idea that I need to mention is this. When we think about, or when we represent fields pictorially, there are 2 ways to do it. One is just draw a bunch of arrows to represent the vector field at various locations. For example, here we've got some positive charge, and let's say at this location, the field has to point that way, because if you were to put a positive charge here, it would feel a repelling force from this one. A positive charge here would be repelled in this direction. So if this is the direction of the force on a positive charge, this is the direction of the field. And likewise, a particle here would feel a repelling force like that. So that's the direction of the field at this point. Is to make things clear, these arrows, as mentioned in the book, these arrows always represent the field at this location here, at the tail end of the arrow. They don't represent field at all these points, just the field at this point. For example, field out here being farther away from the source, still in the same direction, but it's a weaker field because this point is farther away than this field. And then similarly, if we had a negative charge, what does the field direction look like at various points? Here, put a positive charge here and it feels an attracting force from this. A positive charge here is going to feel a force pulling it that way. So that's the direction of the force on a positive charge. So that's the direction of the field at this point. And likewise, any other point, put a positive charge here, it feels an attracting force pulling it towards this thing. Feels a force like that. So if that's the direction of the force on a positive charge, that's the direction of the field. And likewise, if you're farther away, you'd still feel an attracting force pulling to the left, but being farther away, the field is weaker. Okay, so you could represent a field with a bunch of arrows, or these things that we call field lines. In these 2 situations, what the field lines look pretty simple, pretty straightforward, like this. Field lines for the field caused by one lump of positive charge are just all lines that radiate straight out from the from the source. And what these lines mean is that at any location on a line, the field just points along the direction of that line, which is pretty obvious. A positive charge anywhere here is going to be repelled directly away from this source charge. So directly away from the source charge has to be the direction of field, no matter where you are. And similarly, field lines for a field caused by one lump of negative charge are just radial lines, but all pointing towards the source. Because put a positive charge anywhere here and it'll feel an attracting force, in other words, a force pointing towards the source. So electric field at all points here points toward the source. So whenever you draw a field line here, it's going to be a line pointing toward the source. And so for any point on that line, the field points in the direction of that line. If you're interested in a point that actually, a location that doesn't actually have a field line passing through it, you just draw a new field line based on the pattern that you see from the field lines that are already there. Now, these all are like radii of a big circle, and so this would just be the same, pointing straight towards if you wanted to draw a new field line that passes through this point because you're interested in this point, just another line that passes through that point heading straight towards the source charge. Now, one other thing to notice here, and this is maybe the more significant thing that a drawing of field lines tells us. Wherever field lines are closer together, that means that in that region of space the field is stronger. The field has a bigger magnitude. And then just the opposite, you can guess what that is. If the field lines spread farther apart, that corresponds to a weaker field. Implies a weaker field, and that's exactly what we see in these two drawings. Close to the source, the field lines are all closer together. Far from the source, they're spread farther apart, so that means close to the source the field is stronger, and far away the field is weaker. And we already know that's true for the field due to one lump of charge. Write that again. Magnitude of the field due to one lump of charge is k times the magnitude of that charge, distance squared. And of course, as you get closer, d, the distance to the source, gets smaller, so this fraction gets bigger, stronger field, as indicated by this drawing, where if you get closer to the source, field lines are closer together, that indicates stronger field. Okay, that's how, this was just a simple example with straight field lines, but this rule applies again even if you've got curved field lines. For example, if you've got two charges here, the field lines would look something like this. something like that. So one thing we see is that, again, close to a charge, field lines are closer together, indicating stronger field, and then farther away from charges, field lines are farther apart, indicating weaker field. But these lines are curved. In the case of a curved field line, how do you figure out the direction of the field at some point on that line, like let's say this point, because we can't, it's a curved line, so depending on where you are along that line, it's really in a different direction. Well, we just draw a tangent line, the straight tangent line that is tangent to the curve at the curved field line at the point that you're interested in, and then the field points one way or another along that tangent line, and in this case, the field would have to point that way, because the flow of the field lines is basically left to right, and then over here, higher to lower. And then down here, there's a straight tangent line that's tangent to the curved field line at just this point.
Sorry, sir.
And so the field line would lie along this, and because of the flow of the lines, that's the direction of the field. So if the field lines are curved, draw a tangent line to the curve at the point that you're interested in. And again, if you're interested in a point that doesn't have a field line going through it, just draw a new field line. Say you're interested in this point. Based on the pattern that you see here, you can draw a new field line. It's going to look something like that. And so at this point, there's the tangent line. So the field lies one way or the other along that straight tangent line, and because of the flow of field lines, basically left to right, that's the direction of the field at that point. Okay, that's all there was for today.